Welcome back. So we've seen so far that operators in quantum mechanics must be Hermitian, and this is because their eigenvalues are real valued. Operators measure observables which have to be real numbers, so that kind of makes sense. The trade-off is, or the kind of neat trade-off, is that the eigenstates of Hermitian operators, by mathematical definition, are orthonormal and complete, which means they can be used to fully describe a space with linear combinations, and abstract quantum states live in what's known as Hilbert space. And how do we take these linear combinations? Well, here we go. If we take an arbitrary abstract quantum state, let's say ket f, and we know that this ket psi is an eigenvalue of an eigenstate of a particular operator. We take linear combinations in this form here, and we can describe ket f. Now remember, of course, that we can use the inner product to describe these coefficients c sub n. Now these coefficients are just the probability amplitude, and this is just using the generalized scalar product. Now, we're going to use a sleight of hand. And I'll discuss the sleight of hand more in a moment. But really, we're talking about the area under a curve. So this sum, and it's iterating in increments of n, which is 1. So there's a delta n which is being implied here, but we don't usually write it because it's simply 1. We'll come back to that in a moment. The point here is that based on our energy, momentum and position eigenvalue equations, we can describe an arbitrary abstract quantum state, let's say ket sub f, using linear combinations of the eigenstates of position, energy and momentum operators, because they're Hermitian operators. And mathematically, this is what we're talking about. So let's say we take the eigenstates of the energy operator, take linear combinations of those, and you're going to get ket f sub e. And we're saying that this is an arbitrary quantum state that's living in energy Hilbert space. Or we could talk about momentum Hilbert space, or even position Hilbert space. Of course, these c sub n's, these coefficients are known as probability amplitudes, and they can be expressed using the inner product. Now if you look closely, I'm hinting at what the wave function is, but I'll come back to that in the next segment.